Jai Janendra, Namaste and welcome to my channel. Today we are going to solve the 104th question of the problem solving series and the 14th question of the topic tree. The difficulty level for this question is easy and this question has been asked in Microsoft, Amazon, Oracle, Nvidia, EVM, IBM, Apple, Adobe and many other companies. Validate binary search tree. So we are given a tree. We need to tell whether that tree is a binary search tree or not. In the previous question we have seen what is binary search tree and we have searched element in a binary search tree. So here we need to verify whether the tree that is given is a binary search tree or not. So in the binary search tree we know that the left subtree will always be lesser than its root and the right subtree will always be greater than its root, and that property would hold for all the nodes. Okay, since tree is a hierarchical data structure. So let's see this 2 1 3. So its left subtree to 1 is smaller. All the elements are small, has to be smaller than its root. So this is smaller and this is greater. So this is true. We return true. Now this one, second question. Here 4, 4's left is 2. 2 is less than 4. Satisfied. 2's this one left is 1 is again less than 2. And 1 is also less than 4. Right? Now we go here 2's right. Oh, because we don't have anything, this is null, so we go here right. 2's right is 5. 5 is greater than 2, which is correct. But this 5 is actually greater than 4. But 5 is a part of its left subtree. 4's left subtree has these values, and this 5 comes to the left part of this 4. So this has to be smaller. If this is not smaller, then this is false. Say this, so this is false. Another thing, so this is not a binary search tree. Here you can see this part, 6 is greater than 4. Then 3 is less than 6. So 6 is greater than 4. 7 is also greater than 6. The right part. But you see left, this left is 3 is actually lesser than 6. But it had to be more than greater than 4 also, because it is its right part, which is not. So there also the property of binary search tree fails in both the cases. Okay, if it fails in one case, then also it is false. Okay, now how do we solve this? How do we know when we are given a tree it is a valid binary search tree or not? How can we code it? So you can see we have to check for all the nodes whether that property holds or not. Now here if we would have gone here and okay, we would have gone to the left part and see okay, for the left part this follows, the property follows, but here at this one is actually less than 2 and 1 is also less than 4. So for 1, what is the max element that 1 could be? 1 could be actually has to be less than 2, just the next upper part of it, right, from the root, because anything which is below this, okay, we don't know the child's value. The upper part, whatever its root is there and its root is there, for this root, since we are at the left, so this 2 has to be smaller than the 4 and this has to be smaller than this. So for this whatever the value could be, it has to be less than 2, and any value we can give, right, any minimum value it can hold, but it has to be less than its just corresponding root. Okay, so this is one thing to observe. Here also if we see this 6, this has to be anything but greater than 4. Here this has to be anything which is just greater than 4. So when we go to the right, the element, the child element always has to be greater than the root when we are going to the right. But when we are going to the left, the child element has to be smaller than the root. So this is one thing. And what could be the value? It could be any big value. So this is the two things that we are seeing whenever we go back, because we have to verify it for all the properties, all the elements. So we have to use the recursion, we'll have to call this again, but we have that condition that whatever the value is there, if we are going to the left part, then this left has to be less than the root and is less than the root, and it could be any value. It has to be like, it can go anywhere, whatever the value. So just the thing is that for it the maximum value is the root and the minimum value is no limit. And for right, the minimum value is no limit, but the maximum value has to be uh, greater than this root. Okay. Yeah. So it has to be greater than the root. Right. The max value, it could be anything. You can write it over here. It has to be greater than the root. It has to be smaller than the root. Okay. So now let's code it. We'll using this property. We'll code it. Okay. So let's directly call a function return is BST. Okay. Because we need to pass the minimum value, say long mean is the minimum value and long max is the maximum value. Okay. So we pass these two arguments here and we return this. Now we code this function, recursive function is BST, where we have tree node strict root, this root, and then we have int mean or long mean, anything. You can take long mean and long max, right? Or this could be integer or anything, int mean, same thing, doesn't make a difference, right? Now here we see that if root value, if we see that the root value is actually greater than the mean value, less than the mean value, whatever the minimum value is there, or if the root value is greater than the max value, then we return false. Now how you'll understand once I complete the code. Okay. Else return is BST, else if root value is greater than the minimum value. You'll understand. One second, let me code this, and less than the max value. Okay. If it is greater than mean, and what we are passing it, when I'll dry run it for one example, you'll understand. Okay. Then you return is BST. Okay. You return root left. We'll check for the root left part, and for it the minimum value would be the long minimum, whatever the long minimum is there, because it can go anything minimum. Okay. And the maximum is root value, because it cannot cross root value as we have seen, and is BST root is BST root right, it has to be greater than the root, its root value, the right has to be greater than the root value, and it cannot cross any maximum value which is given. You'll understand this. Okay. Else if this is this, if root is equal to null, return true. So now what we have done here, okay, in this 4 lines of code, that we know the property that when we go to the left of the tree, it has to be greater than its root. It has to be lesser than its root. Okay, and it can be any minimum value. Now I understood this, but when I go to its right, this 1's right, 2, 1, 3. Now this 1 has to be greater than this number has to be, since it's right, it has to be greater than its root. Okay, so for it the minimum value is actually the minimum value is actually 1. But what is the maximum value for this? Can it be 5? No. Can it be 3? No. The maximum value is actually this 2. So this part, it cannot be greater than 2. So now that problem is solved when we pass this minimum value and the maximum value. So for this, if there was a, let's code this. Say 5, let's take an example, 5, 4, 7, 3, this is 6, 5, 4, 7, 3, 6, 4, 7, 3, 5, and 6, 9, 8, 10. So now you take this example, okay? Here this is 6, we are at 6. Okay, we get this. This is say minus 1000 and this is 1000, just for the sake of example, okay? Because this is means anything minimum, like long minimum is very like huge number. So 10 to the power something, right? So here if we take it as 1000, minus 1000 and greater than 1000. So when we pass this, so this root value, we know like minus infinite to infinite is will be there. So the beginning, this condition for the root will not come. But if root is null, it is true, right? Because if it's a null, it's a BST by default. So it's true. But if otherwise, else if this condition comes, like if it is less than minus infinite and greater than infinite, then it's false. Here 6 falls under this condition. Less than, it doesn't fall under this condition. It's not less than minus 1000 or not greater than 1000. Okay, just for example. Now, when this condition doesn't come, we check. Okay, that means it comes under this condition. Root value is greater than minimum. So if any of this would have happened, then we would have done this. So here it comes under this condition. So actually we can remove this condition as well. Directly we can return this. Is BST root left, long, mean and root value. Now what we have done, we have went to the left part of it. We need to see, is the left subtree a BST? So when we went to the left, now the left part could be the long minimum, whatever the minimum value is there, that we can be like minus 1000. But what would be the maximum value? It cannot be, condition here is that it just cannot be greater than this 6. So the maximum value is actually, it has to be less than 6, right? That is what we are checking here for this one, okay? This one has to, we have to see, okay? So here root value is less than maximum, so it is okay. So here 4 is less than 6, it's okay, because we are going to the left part of it. So the maximum value when we are going to the left is root value. Okay, now this will be called again. So for now here, this actually instead of minimum, we will be having it as 6 max, because we have changed this min max to root value, which is 6. Now again this should be called going, and this should be going here with this root left. So its root left will go, this 3 will go. So for 3 we will check that, okay, 3 is actually, the left of this is 3 is actually less than so sorry, 4. For 4 is actually less than 6. We have crossed here, we have went here. So 4 comes, 4 is actually less than 6. So our property is valid, and it is not like lesser than minus 1000. So here it works. Now again this calls this left part again. So here when it comes 3 is again less than 4. This becomes 4. Okay. So it's okay. Now this will return. Now if this left is null, so it would return null. It is returned true. Okay, and its right is again null. Once this for 3's left is null, so it would return true, and 3's right is also null. It would return true. So 3 will return true to 4. Okay, and now so for 4 we have went to the left, but we didn't go to its right. So when we go to its right, so at this point the max value was 6. Okay, so for this the max value was 6. For 4 the max value was 6 and the minimum value was 1000. But we are going to its right, this part. So for this part we see that this could be this is actually not mean. This has to be mean. We are passing this mean. Now I've written by mistake. I've written this. This is max. Okay. So this is max. Okay. Now for this one, we saw that when we are going to the right, so the root value is 4. So it has to be greater than this 4, right? So this 5 is actually greater than 4. So it's okay. But this max, for this 4 the max value was 6. So again this max would be actually same. This max what we got for this 4, the 6 called 4, right? And 6 had max as 4 had max as 6. Now 5 is called by 4. So the max value will remain 6 and the minimum value will remain as 4. And fortunately 5 falls between these two values. So the property of BST still remains. So 5 again left is null, right is null, so it would return true, it would also return true. So the left part of this whole thing would return true. So once this is done 6, it would go, this part is done, now it would go to the right part. And for the right part again, the max was long max, not 6. Okay, so it was again minus 1000 and 1000 say. Now again 9, for 9 is, so we go to the 9, so when we go to the 9 here, root right, so the minimum value is 6, root value, and the max value is actually, we passed long max, right? So this doesn't change. So this is 6 actually. Now 9 is actually greater than its minimum value, 6, and the maximum value it is less than that. So it's fine. But it goes to the left part of it. Now when it goes to the left part of it, so it has to be lesser than 9. This value changes, root value. This max which was actually, this max value would change, and the mean value was actually 6. So the 8 has, this value has to be greater than this part. 8 has to be greater than 6 and has to be less than 9 because we are going to the left of it. But it's right, for its right, the max value is actually root value, right? When we are going to the right, so the minimum value is actually the root value, which is 9. So it has to be greater than 9. So in this way, when we are changing the maximum and the minimum value, we make our the code becomes the code actually validates whether the tree that is given to us is a binary search tree or not. I hope you have understood this. The link to the question is given in the description. Please try it yourself and then come to my code walkthrough session. The time complexity obviously would be order of log n. Is the code walkthrough of the 104th question, validate binary search tree in the LeetCode platform. The difficulty level is actually not easy, it's medium level question. These are the questions, these are the companies that have asked these questions. Let's look at the code. We call this value, bool value. Okay, we can directly actually also return this as return BST directly, which I did in the explanation. And here you can see we pass the minimum and the maximum. We check if it is null, we return true. If this is the condition, which is the actually main code, if it is less than min and greater than max, okay, because the root has to be cannot be less than the long min, right? So in the beginning this condition will obviously always be true with the root, but then when we call to the left part of it, the minimum changes, the maximum changes, because the maximum value for the left part of it has to be lesser than its root value, and the minimum could be anything here, like any minimum value it can get. And for the right part, the minimum value will be the root value. It has to be greater than the root value. Okay, right here you can see the right child is less than the left, so it is false. Here the right child is greater than this root, so it's true. So this has to be, this will again be followed. We have already try run the code. I think you have understood it, so we'll just directly submit this. Okay, please draw the recursion stack to understand this better. See you also in the next video where I'll be explaining the 105th question of the problem solving series. Jai Jayendra.